Hello and welcome to this hardware reverse engineering presentation where we explore the depths of a robot vacuum cleaner. This IoT device runs Tizen OS, an open source Samsung Linux lookalike, and runs some proprietary blobs we will analyze with the purposes of repair, fair use, and to regain hardware ownership. Since our time is short, we'll use some AI shortcuts to expedite its file system and binary analysis using the power of R2AI and its Radar2 tooling ecosystem. We'll see core strengths and downsides of this approach and recommend use patterns for LLMs applied to reversing. Prior art from Vale and cleaner hacking pioneers, kudos to them by the way, has not been used in this presentation because there's no Samsung vacuum cleaning devices supported by them. Also, this is an end-of-life device found in the dumpster. Anyway, without further ado, let's get started. We will start with the why, some bootloader and singular manufacturer quirks, and see how much we can extract with AI in a short period of time. And last but not least, establish an SSH to UART bridge with SSH-Stamp. So why is this talk useful to you or the Radar2 community at large? Other than shared values such as curiosity and drive to de-enshittify cloud-connected devices, we objectively improved Radar2 gets, as you can see on those commits. But also, in my previous R2 talks, there were always positive follow-ups within the Radar2 community, providing AVR support, better STM8 disassembly, and today's big ARM binary complexities were addressed within Radar2 core. I would like to give back again to this community and pay forward what I learned and share it with you all. But there's also tactical advantages for, say, InfoSec. Who suspects about a multi-purpose red team vacuum cleaner in your office? In any case, here's today's e-waste menu, Samsung PowerBot VR7000M, which has main brains in the operation, A20 processor, which is a dual Cortex A7. I know it's not the most modern piece of kit, but it serves well for the purposes. Heck, it even has a TV decoder and encoder, as you can see right here. As we have seen in the previous slide, there are several circuit boards in this machine for motor control, power handling, sensor harnesses, etc. But this particular one contains the main Linux software that steers the show and that we will be analyzing. And here are the main IC functions. And interestingly, we have this lower connector that connects to the rest of the machine for communicating with the other boards. So let's begin by soldering a micro USB connector in one of the unpopulated pads on the back of the board. We'll need that for the FEL protocol, a memory flashing fallback system burned into all-winner ROMs. We can flash images or write in RAM and make the processor execute instructions for us. In short, we'll use that protocol to sideload our own U-boot version and ignore the one that is built in. There are two main gotchas with this particular board implementation. One of them is that you must use the USB on-the-go ID, which is the unpopulated pin that you can see here, and you can also see here in the connector, it's not even connected. You must put this into ground and then press 2 in the UART console. But we're having this USB connector, micro USB connector used for FEL protocol. Where is the UART? In many IoT hacking tutorials out there, there's always this 4-pin header that is easily identifiable as a UART. Well, not in this case. There's no clearly labeled pin headers this time. But we have our friend GIMP, so let's keep calm and draw some pictures. First, we go to our favorite all-winner datasheet. We identify the UART on the actual ball grid array IC, and then we do a scan of both sides of the board to overlay where more or less would those pins be. We overlay the datasheet VGA image, and then we identify that somewhere over there must be a UART RX and TX. And we try our luck probing. What happens next? We get a successful bootlog from it. And this is Titan 2.3.0 and our Samsung Linux platform, greeting us with a logging prompt. What shall we do next? Next up is learning a little bit about U-Boot. I cannot cover this in this presentation, but I wholeheartedly recommend this really good U-Boot book that doesn't cover our all-winner specific details, but it gives a really good overview on how to hack U-Boot and also protect against common attacks. For sure, there's more than one way to hack this, but the way I chose to access this device's file system was to compile my own U-Boot via similar OpenWRT supported A20 all-winner board and use the FEL protocol to upload the resulting U-Boot binary into the board's RAM and execute it. The SSH tools command above does exactly that. And as you can see by the U-Boot log, it boots successfully into a U-Boot prompt. But what's the Ethernet error, you may ask? So even if we got a successful U-Boot shell prompt, we have to be careful on how we do those things because the Olimex A20 board definition found in OpenWRT differs from this particular one. And I was actually lucky I didn't find any device in the board. Those differences might have been different settings on voltage regulators, and this could have fried some of the devices in the board. There's this custom format called FEX that is used to define or describe how early the RAM and other peripherals are initialized at boot time. This FEX custom format is found under the file system /boot/sysconfig.bin, and this sysconfig bin can be transformed into a readable format called FEX, and asking ChatGPT to transform this FEX into a compliant DTS is something that you can do, as you can see here. Now, one of the main reasons I focused on building my own U-Boot was that I needed two commands at the U-Boot level, ls and cat. With those two commands, you can list the contents of the file system that is in the flash memory and also do a cat or a dump of those files directly in the shell. So it's nice to just like poke around text files directly from U-Boot in a data forensics and information recovery fashion without affecting or potentially corrupting the file system underneath. But first, the board had to grow another USB port. I had to do away with the built-in Wi-Fi dongle that was connected to this connector and just solder in with a little bit of butchering, but it works, of my custom USB pen drive accepting connector. Since doing cat on non-text files is challenging from U-Boot, next step is to try to exfiltrate the contents of the MMC or flash file system into an external USB pen drive. And this Rust snippet shows you the technique in a nutshell. You essentially read from several sectors in a defined chunk size from the flash memory and then dump into the USB using an intermediary RAM address for the copy buffer. So I merely connect the pen drive to my new jig, and then reads and writes start to flow, and then errors start to come out on the USB bus. What gives? This is a very new U-Boot release, so why is it erroring out? Must be my soldering, right? Nope, it wasn't the soldering, it is software. Well, software and hardware. It turns out that not all USB pen drives are created equal. So there's some pen drives that misbehave and make the bus not respond. And this poor developer, U-boot developer, complains about this fact. There's many other boards, by the way, that exhibit the same behavior. From Jetsons to NXP, different boards, different versions, and there's a common thread, and this U-boot issues have not been fixed. So after looking at different patches and trying to hot patch my U-boot build, I realized that I haven't tried the easiest way, which is just swap the bad pen drive with a newer one. But this bad pen drive works on many other devices without a problem. This one, although, works with our target device. So just with a few reads and writes, the dump was successful. So we have 4 gigabytes of the file system dumped with this technique. So we have 4 gigabytes of file system to go through. Where do we start? Well, here's like a small selection of the file system. I just put it in a different directory. And we'll just poke around, look at how things are organized, more or less. What are those scripts? Oh, what is executed at boot time? Maybe we can do RC, init, smack utils. What is this smack utils? Oh, maybe it's like this kind of SLLs equivalent that Samsung chose to secure their systems with. Well, as you can see, we can spend a long time looking for libraries, binaries, and different ways to skin this cat. So how would LLM output help us in this situation? Using LLMs or R2AI or MI or the rather toolset, we would get this kind of result files given some queries as like, please help me find what this file system has interesting binaries for me. And it will generate such a summary where we can see almost immediately which files we should focus on. It says like Max is a RVC or robot vacuum cleaner main binary that we might be interested in. Something to do with the cameras of the robot, something to do with planning and of the paths and power systems and the different things. This would take quite a bit of time to do manually, but with LLMs we can get this nice summary with a single prompt and waiting for a few seconds. How will it look like in the context of R2? Well, as you can do in plain R2, you can see the imports or list them. And just manually look if there's some like DLOpen libraries being called. But we can expand the knowledge or deepen the knowledge of the linked imports or libraries, third-party libraries, using this particular prompt. So we have the provider OpenAI with this model, and then we tell the AI to explain which imports belong to which library and describe its purpose and scope, and we just throw in emojis for fun. Pretty much everyone in the audience knows what libstdc and stdc++ does, so just let's skip through a little bit. But here the interesting libraries are the ones that come from the vendor. In this case, the libcapi, which RVC, that would be the remote view camera or the robot vacuum cleaner. Please mind that some LLMs can hallucinate. For instance, if we don't give enough context, this libcss could be confused by cascading style sheets. But here it has correctly identified that is a camera subsystem. and more like hardware-related low-level abstractions such EEPROM, sound system, logging system, etc., etc. So this also would take quite a bit of time to figure out manually. So if you're familiar with reverse engineering C++ binaries, there's this facility in Radar 2 for displaying class information. This can be augmented by AI using my piping the output of those classes found in the max binary to my asking the AI to create a C++ class definition for those methods. And then it will generate an output CPP that kind of resembles what we're looking for, instead of having to navigate through complex class definitions. And yet, sooner rather than later, we start to realize that there are limitations with this approach, namely that the generated code needs a significant effort to be reviewed and validated, although we can just like feed it back to the LLM and try to make it nicer and summarize the outcomes. But also, we need to also cross it with like actual, in our case, types and sources. So this is more like future work rather than limitations. In summary, there's the realization that every binary needs some custom treatment eventually. And there are many so-called like skills that can be taught to the AI and to the LLMs and fine tunings. But at the end of the day, they should be a human pilot behind the wheel. After our several findings and seeing that there's more future work to do, it's time to design a more permanent solution where we don't have to have wires hanging around on a mobile device like a robot vacuum cleaner that can be moving around. We have to design something that we can access to the UART and flies remotely. So here I scanned the board itself and I just designed an outline, a so-called hat, that is gonna be sitting just on top of the board that we have as a target. And those different vias are gonna be pogo pins that connect directly to the board. And this expressive wireless chip is the one that we're gonna be using to access the UART. And here's like a little bit of a reality check with an acrylic plate and the pogo pins sticking with nail polish, which clearly needs more iterations to be a little bit better. To be clear, I'm not selling those PCBs, but if anyone is interested, just reach me out and I will be happy to hand out the design files. Regarding the software that is going to be running on that expressive chip, I have this other project that is called SSH-Stamp, which is essentially a SSH to UART bridge, and that fits perfectly with the current use case. We can essentially SSH into IP, and then it will show in the console all the UART output from the board that we are targeting. So how does the road ahead look like for this project? Well, I would probably adapt the PCB hat to reach some other peripherals that this board might be exposing, potentially port it to Vali2, fix the device tree, and even upstream the board being called Cleaner A20. And for R2, potentially find some patterns, some LLM patterns that can be extracted in a generic way to analyze C++ binaries, especially big ones that can be problematic for LLM input. parameters, or so-called like the input context. Last but not least, I would like to thank Pancake for giving me the chance to present in this talk, and I hope that everyone in the audience liked what I had to say about hardware, LLMs, Radar 2, and whatnot. And since the topic of this conference is getting bad roots, please use email instead of social media to contact me if you want. Goodbye.